Well, greetings, Earthlings. We're going to be learning today about classifications of stars and characteristics of stars. And this kind of ties along with what we've been learning about our own sun. So let's get started. First of all, stars are classified really just using 4 different characteristics that they have. And it seems pretty easy to think about it this way, but stars are hard to think about being classified in just 4 different ways. But they're so far away that it makes it easier for us as humans to kind of help classify and organize the stars that we see into different groups so that we can better understand them. So they're sorted out by color and temperature, size, composition, which means what are they made of, and then their brightness. When we think about the color and temperature of a star, it's really related, the color of a star is directly related to the temperature, how hot or how cold it is. Hotter stars appear to be a bluish color, which seems kind of strange. We would kind of think it would be hot. But think about if you've ever looked at a candle up close, and you can see the hottest part of the flame is actually right around where the wick is at, and it's usually kind of a bluish color. So it's kind of just related to what a star is like. Cooler stars appear reddish in color, and you have in between kind of fading from blue to kind of a pale yellow, then a brighter yellow on up to red, being the actual coolest. And our sun, since it's yellow, fits into this classification. So down here is the different colors and the different letters that they give these colors. So this is it, the hottest stars are in the class O, and their temperatures run between 28 and 50,000 degrees. Okay, next way that we classify stars is by their size. So many of the stars in our sky are the same size as our sun, which is a medium-sized star. White dwarf stars are about the size of planet Earth. And then red giants and supergiants are they're the largest style of stars, and they are so big that they would fill our solar system all the way out to Jupiter. So then we think about what is the composition of the star as another way of classifying it, and that's through its chemical composition. So most stars are 73% hydrogen, and the abbreviation for hydrogen is H. They're 25% helium, and its abbreviation is He. And then 2% of a star is other elements, like perhaps carbon or other gases that might be there. And how do we know this? Is we use tools called spectrographs. And these spectrographs basically break down the light into colors that the star is producing, and then they produce an image of those colors, which then represent what different elements the star is made of. And you'll probably get more into that as you get into 7th and 8th grade science. Okay, another way to classify stars is by their brightness. Now, brightness is determined or figured out by both a star's size and its temperature. And then we think about 2 brightnesses. First, we have apparent brightness. And apparent brightness is just the brightness as it's seen from here on Earth. So that's kind of like what we looked at the other day with our slide, where one star seemed to be really, really bright and one wasn't as bright. Well, really, it was just because one was closer. So even apparent brightness has to do with being closer to us than others. But then we have what's called absolute brightness. And this is the brightness a star would have if it were just a standard distance from Earth. So if all the stars in the galaxy were lined up the exact same distance from Earth, there would be some stars that are brighter than others. And that would be their absolute brightness. So if we're going to measure the distance to a star, also to help us classify it, we use a unit of measurement called the light year. And it's used by astronomers to measure the distance between stars. And a light year is just the distance that light travels in 1 year. And that's kind of tricky because it's really just 1 Earth year. So if we were going to measure distance to stars, we have to use something called parallax. And parallax is just the way something changes it visually apparent in the position of an object when you look at it from different places. So if you're standing over here at letter A, and we look at C, the tree, it's going to look different than if you're standing over here at B and looking at that tree because of where you're standing. Now, if you're standing at B and you're looking over here at this house, it's definitely going to appear different than if you're standing at A. You'll see some different things. Same thing here. If you just look straight out past this little tree from A, you might not be able to see these two trees. And if you're standing over here at B, you might not see all of the house because this tree might be in your way just a little bit. So parallax is the change that happens if you move from here to here. So astronomers measure distance to stars, and they use that same idea of parallax, only they use nearby stars to determine the distance of another star. So here we have Earth in December and Earth in June, and we look at that star from this direction and from this direction, and we would see these behind it more different during different times of the year. So here's what it would look like. From Earth in June, the pink star would be visible, and the blue and the green would be visible down here. But when we switch to December, stars are different looking, even though they really haven't moved. We have. So we have a different alignment of stars. So the less the star appears to move, the farther it is away from Earth. Okay, we have another classification system for stars. It's over 100 years old. And scientists still use this diagram to help classify it. It's called the Hertzsprung-Russell diagram. The main sequence of and they call it the HR diagram, so because nobody wants to say Hertzsprung-Russell, is this diagonal area right here. So this is where most stars tend to land. So you can see there's some blue, and there's some yellows, and there's some reds. And these are what we call main sequence stars because they're the main area on the diagram. It contains almost 90% of all stars that we can see. So you can see though out here, outside of the main sequence, there's some bright stars that are big, red supergiants and red giants. There's also the blue giants. And then down here we have the white dwarfs. Here's the same diagram a little bit closer so you can kind of see it. So, and look, there's some exponents. So if we look here, 1 represents our sun, okay? So our sun is over in here somewhere. And 10 to the second power means it's going to be 10 to the second times brighter than our star, so it's going to go up. 10 to the fourth means it's 10 to the fourth times brighter than our star, So that would be really, really bright. 10 to the 6, even brighter. But the opposite way, 10 to the negative power, means that they're going to get not as bright. And same thing here, okay? Then down here is its temperature. So we really haven't found too many stars that are over here in the 40,000 degree mark. And this is not degrees Fahrenheit. We'll talk about that measurement here. Really what you need to know is that they're going to get cooler on this side and hotter on this side. And you can tell just by the numbers increasing. So again, here's those white dwarfs. They're small and they're not very bright, but boy are they hot. Same thing up here with the supergiants. They're not as warm as the white dwarfs, but they are definitely brighter and they're bigger. All right. Hope you got some good notes. If you didn't, go back and watch something that you want to. Be sure you turn in your note-taking sheet today. And if you don't get done with it, you have some homework over the weekend. Make sure you take it home and get it done. Thanks, guys.